Now, what we've learned is that the average number of solutions of a random formula gets exponentially small when alpha is bigger than a number which is 5.19. Now, think a little bit about what the average number of solutions tells us. Here is a basic fact from discrete probability. If z is a random variable which counts things, its possible values are natural numbers, non-negative integers, 0, 1, 2, and so on, such as the number of solutions to a random formula, well, there's a handy inequality. Some people call it Markov's inequality, but in some sense it's even easier than that. It says that the probability that z is bigger than 0, which in this case is the probability that there is at least one solution, the probability that the random formula is satisfiable, is less than or equal to the average number of solutions. If you've never seen that before, I urge you to think about it as an exercise. It's not hard to prove. But so this gives us a rigorous upper bound on the probability of satisfiability. This means that as soon as the density is bigger than 5.19, a random formula at that density is almost certainly unsatisfiable. But the actual threshold, measured by excellent numerical experiments and backed up by calculations from physics, is noticeably lower. It's 4.27, not 5.19. That's kind of interesting. What that means is that for densities in between the true threshold, 4.27, and our calculation from the average number of solutions, 5.19, in between here, the average number of solutions is actually enormous. It's exponentially large, and yet, most of the time, there aren't any. Somehow it's 0 almost all the time, even though its average is large, because we're above the threshold and we're almost certainly unsatisfiable. How could this possibly be? This is another quiz for you. What's going on in that middle zone?